Okay. Welcome everyone to the Manchester Java community this evening. So we're live on YouTube this evening, which is a first for us. So a bit of an experiment. Hopefully it goes well. Before we get into the content of tonight's session, just want to mention the JManc conference is coming up on Saturday, the 22nd of October. This is based in Manchester, UK. It's based in Manchester city centre. It's supporting a local charity called Jamie Horrocks Trust, so all proceeds from ticket sales will go to that charity, which is amazing. We've got some great support from a couple of big sponsors, Ecom and Sainsbury's in Manchester, and also some from the Java community, Azure, Hazelcast, Piara, JetBrains, Sonatype, and the London Java community and RecWorks as well. If you want to find out more details, please head over to jmanc.org and check it out. So on to tonight's session. We've got Dennis Makogon he's an Oracle developer advocate. I suppose nothing more to say from me. Over to you, Dennis.
Thank you so much. Thank you for having me here at Manchester Java. My name is Dennis Makogon. I'm a principal member of a technical staff and Java advocate at Oracle. I'm also practicing cloud solution architect and Java developer by nature, as many of you are. And also, I'm an awarded landscape photographer. I also run a project known as Northern Lights Awards. It's an application written in pure Java that analyzes the data and telling you which country was the best one to go and witness the Northern Lights. And this kind of award was established since 2019 and still runs up until this year. So we're pretty close to the next season of the Northern Lights. So today, I'd like to talk about building Java applications with native code using Project Panama. We're pretty short on time, so let's get to the point. For quite a long time, developers have been using a technology called Java Native Interface, a solution that allows to bring native code into Java applications. First and foremost, the foremost advantage of such technology is that it allows to bring solutions that either weren't available in Java ecosystem nor implemented, nor possible to implement in Java. Its powerful and its power and a weakness is that the code that implements JNI is very platform specific. So the purpose of Project Panama is to change the way developers interact with the native code from the inside of Java applications. In this talk, I'll cover both foreign functions memory APIs and Jextract, leaving the vectors API for another time. So foreign functions and memory API, which is a part of the JDK 19 upcoming release in less than a week, offer a variety of new APIs that attempt to give an answer to the following questions: how to invoke a native function in a particular signature by its name, and how to let a native code call back to Java application. Every of these highlighted words correspond to a particular API class that is a member of foreign functions and memory API. Let's start with a linker. In terms of the computer science, it is an implementation of an application binary interface, which purpose is to provide necessary capabilities to perform both down calls from a higher level system to the lower level system, and up calls in the opposite direction. For instance, invoking C code from the JVM and letting C code invoke Java code. That's what the up call is. So linker implementation, the current implementation of a linker supports different platforms, including Windows, Linux, and macOS, including the latest ARM chips, ARM 64 chip architecture, and etc. So if you even have a latest Apple M1 laptop, it will work there as well, and on any ARM server that you probably could run on the cloud. While the linker answer to a question how to call a function that you have, a simple linker is more about to find the function by providing an interface for searching an address of a function by its name. At the same time, it gives an answer where the function is located inside of a shared library or a standard library, any third-party shared library or within a C standard library. It doesn't give a hint what kind of function that is. Which means there is no type being associated to that function. So function descriptor API class is the way to describe what's the type of a function we'd like to invoke by describing the signature of a function that consists of a return type, positional, and variadic arguments, which is known in Java as var args. Similarly to the JVM that has no idea what the type of a native function it will invoke, C code or native C code has no idea what types Java has. So when the Java application crosses the border by stepping into the world of a native code, it has to explain to C what's the data it passing back and forth. That's why foreign functions in memory API offer a set of value layouts which use to sketch out an off-heap memory persistence that can be identified by the C code. It means that inside of a JDK, you have a layouts that map to the C code, and then when you will structure your Java variables, you will know how exactly pack the data in form of like a byte arrays that will be clearly identified by the C code in a specific type. But that could be native types like Boolean, floats, integers, longs, longs, and etc. And that's the only way to let C understand what Java variables are by sketching out their layouts using Java code. Instead of following the same programming model as with the JNI, foreign functions and memory APIs provide a different angle view to the native code invocation. So the foreign function memory API provide method handles as strongly typed, directly executable objects to the native symbols using the constructed object by the native by the segment of by the segment of memory that points to the particular function, and a function descriptor that describes what kind of function that is. A new type, the function descriptor forms a new type of a resource that tells to the JVM what method type and what type a method handle must have in order to comply with the original C function signature. It actually means that when you code, both method handles and so if you're familiar with the Java reflection frameworks, you probably know that there are method handles and var handles for that map that work exactly with class attributes or class methods. So the both method handles and var handles are new to Java system. These classes form a skeleton of the JDK reflection framework. They're designed to provide an access to Java methods and class attributes, so no matter what kind of access mode they were defined with. So before Panama, we had to work with the Java native code, native method, native when you have to put a special keyword in the beginning of a function declaration. So the JVM was responsible for creating harness between C functions for the JNI and Java methods. So developer would have to only write the C code, compile it in the share library, and then tell the JVM that this code actually maps to this particular native method by just adding the keyword, the native keyword to Java methods. But now developers will be responsible for optimized method handles pointing to the exact C functions. A more interesting concept is an up call. While the down calls allow to invoke some native code, up calls allow lower level systems like C or C++ to invoke Java code. In C, as you know, we didn't have something like a function type, which is the thing for Java. You have functional interface, and in C you also have a class named function. However, we can create a pointer type that can correspond to the one or many C functions that can be invoked through it. So similarly to the down call, using the linker, we can construct a pointer to Java method through a method handle that mapped as a pointer residing on off-heap memory. And that memory address is what C function can use as a function pointer to invoke Java methods. It does seem complex, or maybe not, but actually it is. The biggest question, and probably the most important one, is how to manage the off-heap memory within the JVM. So off-heap memory, also known as a native memory, so that's a piece of memory that is not a part of heap, but is the rest of the memory that the user space within the operating system has. So you see, almost every aspect of writing Java applications that use native code is somehow bound to native or an off-heap memory management. If some of you have worked with a JNI before, you know that there was a need to properly manage memory in the same way because the JNI code is mostly C code, so you had to use a similar combination of malloc, calloc, realloc, and free C functions. This isn't a thing to Panama, as it offers a way to deallocate memory segments once they no longer need it, thanks to a garbage collector and try with resource code construction. At the same time, developer can use more advanced memory allocation techniques using a class called segment allocator that allow to allocate a memory arena, basically a large fixed size piece of memory. Note that a term arena isn't Java specific. It actually came from the C++ for a long time ago. Often these arenas, like big chunks of big fixed size pieces of chunks of memory, used in a segment per task use case. So in those use cases, when you know that this particular piece of code or a function will need, let's say, like 1,000 bytes, you can allocate that memory at the very beginning and then use the segment to allocate from it for any variables within this function. So the segment per task use cases, by the end of which, these are segment per task use cases, by the end of which the only thing that is necessary to do is to reclaim the whole segment in one go instead of per variable reclamation. So as you know, if you will do the same stuff in C, you will have to allocate using malloc. You will have to allocate a portion of memory, and then using the byte-array slicing, you can allocate. You can cut out some pieces of that array for the particular variables, but then you didn't have to call a free function against every variable. All you have to do is to reclaim the whole arena in one go. So it actually makes the whole execution free. I mean, like the whole memory allocation within the arena is kind of free because the amount of operations is very minimum comparing to the malloc. So, and the only thing you have to do is to remain like an index of the next free byte within the arena, and then once you're done with the increment in that index, it means that your arena is done, and you no longer have a free memory to allocate within that arena. So segment allocator in Java is kind of a lower level memory management API, similarly to C or C++. which isn't a replacement to a memory session, but rather a way to manage a memory arenas at once using the same allocation methods. So the memory session can literally do the same as the segment allocator, but it can work against all available off-heap memory, while the segment allocator often used to work against arenas. So yes, in Java code, you can create a segment allocator that is bound to a memory session and just use the same amount of memory, but it's not like a typical use case, a typical workflow how to work with a segment allocator. But in this situation, you often should use segment allocator to work with arenas. But if you want to work with the amount of memory that may constantly be changing, because you on your operating system, you may have multiple processes that also consume that memory. So you're not guaranteed to have enough memory available in the next time when you will call a memory session to allocate you a segment of a particular size. But that wouldn't be a thing for the segment allocator because it will allocate you enough memory, and then you'll be guaranteed that you have enough to keep the allocation going within your operation. That should be something like a segment per task uh, uh, procedure. So you see, there are two different programming models nowadays. You have a pure C++ that involves conscious memory management, including malloc, realloc, and free. You have JNI, which is mostly C, but with JVM harness. But still, you have lots of C code, and it also adds a complexity because you have to manage a special C types that map to the type that JVM is operating by. And now we have a Panama style, where a developer taking taking more responsibility than that was a thing in the previous ones. Meaning, a developer will be responsible for creating the infrastructure code, making sure that the code is optimized and efficient. But there is one major change in Java code. A developer has to do what a C compiler does with C code. It means it has to create a compiled approximate or the exact invocation layout for the C function. That's a major change in the experience you might not expect to have in Java, but we aren't only the ones in this boat. Every programming language that decided to adopt application binary interface concept forces developers to do is exactly the same. And anyways, the most important part in Panama is still linker. It actually acts like a C compiler, which correlates with what I said just before. It compiles invocations to native functions with a bit of help of a JIT compiler. And let me explain this in details. Let's look at the simple C application. We all know a simple application on the slide. We all know that variadic functions and methods are in Java. We all know that variadic arguments and methods presented in Java, but in C they are different. In Java, variadic arguments or var args support is a runtime feature handled by the JVM, but in C it's a compile time feature. So the variadic function exists only in the code of the C code text. At compile time, this function will turn into a special variant of themselves, but with the exact argument types, order, and the quantity of the arguments. So that's the responsibility of a developer is. So the responsibility of a developer is to create a specialized variants of the same variadic functions that will match to the exact combination of the variadic arguments, types, order, and quantity, similarly to what a C compiler does. So in the previous slide, you've seen that we have multiple invocations of the, let's say, printf. And when a compiler will compile that code, it wouldn't create just one function which named as printf. It will create three different functions that will have a different argument layouts. And that's what a Java developer will have to do with Panama by mimicking the work of the C compiler using the linker. So that's That's not like, so it does seem to be a complex. It does seem to ask you to do a lot more work by creating infrastructure code, but that's not the downside of the application binary interface. No matter where you're facing, you're working with that interface, but something that developer have to live with. Therefore, developer responsible for not the invocations, but for the rest of the components that make a native code execution possible. And as you already seen, that every invocation to a native function consists a list of three attributes, three objects. First is a memory segment where the function, when the C function resides. You have a function descriptor that describes what kind of function that is, meaning the type of a function. And then you have a method handle that combines all these two and creates an invocation, the strongly typed invocation object that can be used to invoke a specific native function. So that's what developer will have to do. But the most important thing that infrastructure code that consists of a method handles, link, function descriptor must be performance effective, which means a linker, descriptor, method handle must be constant, so the JIT compiler can go and optimize that code as heavy as possible to make further native code execution cheap for the runtime. If it's not the thing, a JIT compiler optimization isn't possible for dynamic code. So it makes the execution as expensive as with the JNI. So it's either a choice of flexibility, parameterized based method handles, or the performance when you have everything in form of a constant, so the JIT compiler can process that in the best way. But the good thing is that infrastructure code is mostly written once and not very often revisited. So the choice of the better performance is much more appreciated, which means that we do not often change library versions, which means if we can write that infrastructure code only once and then revisit that on the new major or minor version, but only by the moment when the signature of the underlying C share library when the API of the library will change, and we have to reflect that in Java code. So the only thing that may require a developer to change the infrastructure code, unless is the underlying, so the only thing that may require a developer to change the infrastructure code is a library change. So it could be multiple cases. It could be a signature change, it could be a structure change, it could be type def change, or even macro change. But so there's a way to make life much simpler. So the Project Panama offer a new standalone GTK code tool called Jextract. Jextract isn't a part of GTK distribution because the target audience of that isn't that wide, similarly to the JNI. Like, not many developers have noticed that with the move from Java 8, one of the code tools has gone, which was known as Java H, and now its functionality is a part of Java compiler, but using the -H flag. So whoever needs Jextract, it will find a way to download the binary. And it's also interesting that Jextract isn't a single binary executable, but a linked Java runtime that consists of the additional GTK module that holds the implementation of a new code tool and some of the workflows. But the fact that Jextract is a standalone, because it will not be shipped with the GTK 19 because the binary itself is the distribution is big, because Jextract actually depends on CLang LLVM, which is big. If you're going to go to GitHub and check the release, you will notice that every new release of the LLVM is growing, and for now it's more than 500 megabytes for the release. And when you compile the Jextract or download it from the Java, the jdk.java.net/Jextract, you will see that the size of the archive distribution is nearly 200 megabytes. So just imagine that you have a JDK which a bit more than 300 megabytes, and then you have additional 200 megabytes of Jextract. So that's why the Jextract is being shipped as a separate tool. So what's this all about? Jextract can generate you a Java package that contain the infrastructure code for native symbols defined in a target C header file. So if you want to generate, let's say, a code for C standard library, let's say for stdio or group or passivity, you can use Jextract to point to a specific header file, and then using the clang, Jextract will parse header file and then extract every native symbol which is mentioned in that header file. So if in the header file you have, let's say, another includes, Jextract will also go to those includes and then will extract whatever it can. But there are some limitations. For instance, Jextract can only extract those types that could be mapped onto the Java types, which means you don't have a longer types. For instance, you don't have float double precision. You also don't have, as far as I can recall, long type. But eventually, at some point, it will change because we're still waiting for Java native types to appear as part of the JDK in the future releases. So instead of writing tons of code that I've showed you before, which includes a linker, function descriptors, and etc., you can only tell the Jextract that you want to create Java code for that library, and then you will get a package that contains a single that has multiple classes, but you have only one public API class that basically represent a header file that you use to generate that code. And worth to say that Jextract offer a good level of code optimizations because it creates constants for method handles with one exception. Variadic functions are the exempt from this rule because Jextract tries to be a good fellow and provide a dynamic parameter-based solution to native functions. What does it mean? So for functions like printf, it will create a specific handle that will try to guess what kind of a parameters it received for the variadic arguments, and then we'll try to build a new variant of a method handle by recreating a function descriptor that matches to consists of the layouts of layout types of those parameters that are being used to invoke this function. And then all that code will try to assemble a new method handle to comply with the invocation signature. It's not the most effective solution, but it's a dynamic solution for sure. And previously, I've shown you that in some ways you can create a constant that represent a specific type of a variadic function by explicitly declaring what kind of arguments this particular function can handle. And it means that if a function descriptor defined in that way, it means that a method handle used to that was created from this function descriptor would not be able to handle a different combination of parameters, and a specific exception will be thrown saying that a method type of a function of a method handle doesn't correspond. The invocation method type doesn't correspond to the method type used to create a specific method handle. So Jextract will create a custom array collecting variant of a method handle, they will try to guess what are the carrier types of what the carrier types of parameters used to invoke a native function to reconstruct both function descriptor and the method handle to match those parameters. This code, as I said, isn't effective because it makes every piece of the infrastructure code that form at a native call dynamic, which means that the JIT compiler wouldn't be able to optimize that code effectively. So such solution indeed works as expected, and believe the people who stand behind that, they are smartest engineers I know. However, it makes the whole infrastructure code dynamic. Therefore, an invocation becomes, once again, expensive, which means that you will have to invoke that type of a function as many times as possible, but the same combination of arguments in order to trigger the JIT compiler to make that invocation more effective. Because this solution is based on the fact that we need to guess what inside of the object array then being passed as Java var args that hold the exact invocation parameters. Object types, order, and the quantity. So you either agree with less optimization, less optimized variadic functions, but with truly dynamic variadic arguments, or heavily optimized C2 compiler constants, but with a specialized method handles for each combination of positional and variadic arguments. There are a few good use cases that already using Jextract and foreign function memory APIs in production. For instance, a library called OpenGL for Java, or Panama GL. It basically takes OpenGL C API and then creates a Java classes for it, and then you can start using that library directly from Java application. That's what it's all about. Also, if you're familiar with the machine learning, you also know about the Onyx runtime. It also offers a C API, so you can create a specific version. You can create a Java library for Onyx runtime, but be aware that for Onyx runtime is very specific for different platforms. So you have to be aware for what kind of platform, what kind of API you're generating, because even though Java code is you can write it once and run it anywhere. But in this case, you're working with a very platform-specific stuff, which may not be available in a different platform. Let's say Onyx runtime for Linux can only work with the CPU, but for Onyx runtime for Onyx runtime for macOS can only work with the CPU, and Onyx runtime for Linux it can work with the GPU. So the code generated for Linux and for macOS may not be the same and may not even work in the same way. And the most interesting one, that Jextract was built using Jextract, which means the Jextract is the first consumer of itself. If you go to the Jextract GitHub repository, you will notice that the structure of a code generated for, let's say, C standard library and for the Jextract, they match, which means that in the very early stages, Jextract was written manually, but then when it's matured to a specific up to a specific point, it was used to generate Java APIs for a C-lang library, libc-lang library. So now, which means that the first application or the first product that will match a regression, that will face the regression if something will go wrong, would be Jextract. So if you're going to use that in your own applications to generate Java classes, you won't be the first one who will notice the errors with the Jextract. What are the known issues for now? It's all sound quite interesting and indeed entertaining, but I had to admit that the world isn't that bright and sunny as we expect it to be. Unfortunately, Project Panama can only work with C++ code indirectly through a procedure known as type degrading. What it means. For instance, in C++, you have a class, you have inline methods, but in C, you only have structs, functions that can work with a struct through a pointer instead of, for instance, instead of vectors in C++, you have only arrays in C, and of course, no C++ templates, which is, I would say, bummer, but C was never designed to have templates. That's why we have C++. So you see, there are more disadvantages than benefits. Another, and yet the most powerful solution around that, instead of a degrading the type, for instance, from a vector to the array, there is a way to build. So the whole solution is built around unassociated C pointers, whereas C++ allowed to construct a pointer that doesn't have type, or it actually has type. It's called void type, or also known as broad type. It's an encapsulated memory segment that stores a pointer to a variable of a specific type. So in C++, you can create an associated pointer that basically represent just a memory, but not a specific type. So you can create an associated pointer for whatever C++ class you want to create it for, and then and that helps to reconstruct the same type once there is a need to get back to the C++ class instance and their APIs. So stepping away from the C++ type with the broad pointers gives more flexibility to actually make Java code be able to talk to C++ code without type degrading, as I described before, nor any other conversions leading to poorly performing code accompanied by ugly C code. But still required to create many C methods that wrap C++ classes APIs to make them exportable and consumable in Java. I'm not going to talk about other solutions like write it in C, let Java run it for you, whereas the most code is written in C and that being done in C while part of Java is a thing as possible. Taking all these techniques into the account, you see that indirect access to C++ code isn't that really a problem of Project Panama, but rather than an LVM problem, because it offers a poor interface into the C++ code. So no matter what kind of a code it compiles, there isn't such thing as an intermediate C code. If you have worked with a LLVM, you know that you can compile C code into the machine code directly, but you didn't have like any intermediate stage where you can basically from where you can get a more sane output than the machine code. So the LLVM and any other tools that turn C++ code into C code, that would be possibly a game changer to Java ecosystem, because as you know, or may have seen, most popular Java libraries nowadays being written in C++ and have deprecated C API not so long ago, or even haven't been started, or even didn't have that at any time. So such tool will help to benefit the whole Java ecosystem. The whole Java ecosystem will benefit from a tool that will help to take C++ code and then transform it into the C code. And then from there, we can use Jextract to create a Java classes for it. But for now, there isn't such a thing except the one that basically takes C++ code, compiles that into WebAssembly, and then you can decompile from the WebAssembly into C code, which is definitely doesn't work or nor will be a choice of any developer I know. So if you're interested in this topic, I'm happy to guide you through and help you to identify your problems or help you to figure out how to work with the C++ code, because it's kind of hot topic. Because if you're gonna go and see what are the most popular libraries nowadays, you probably would see that most of them are C++ libraries. And now there's a question. Okay, we're having Panama and Jextract releasing in less than a week. How can we start working with C++ code? Because that would be the question just a minute after the release. And now we're looking in a way to identify what are the potential solutions to that. And we have tried multiple ones, but found that the unassociating pointers is probably the most effective way, because if you have a pointer just to a memory segment, it would be the same entity in Java. So you don't have to worry on how to transform C++ class into Java class. That problem just goes away. You need to just understand that how can you work with that memory segment, how you can transform it back to the original C++ on the C side, on the C side within the C shared library with source code, call it whatever. So yeah, that's pretty much one of the hottest solution right now, and we're looking into building a prototype that will help developers to make first steps towards C++ code, but not only to the C code, which is, as you have seen, it's relatively easy to start working with a Panama, or with Panama directly using foreign functions and memory APIs, or using the Jextract to actually generate Java classes for the native code, and then just use it. So anyways, I think we're pretty done for today. So if you have any questions, I'm pretty open for them right now. Thank you.
Awesome. Thanks, Dennis. There are a couple of questions. So one of the questions is all this covered in JEP 419?
There are so for yes, most of the things are being described in the latest JEP, which implementation will be included in the JDK 19. But as you may have seen that the APIs that represent function descriptor, linker, and etc. are being integrated into JDK a few releases ago, and they have passed through some modification stages. And for now, you can start using that, but you have to be aware that it will be still a preview feature, but not a standard feature. So, but it shouldn't stop you from using the code, because we already use this, let's say, in some of the applications we have developed internally. And of course, as you've seen in the examples, you can, if you're going to talk a bit about like vectors API, you know that you have vectors API in C++, mostly in C++, and from there you can start. You can create a code that will wrap vectors API, the C++ vectors API, no matter what kind of processor you're working on. You can wrap that into the C API and then use that from inside of application. But obviously, you can use directly vectors API from the JDK right now, because it will be published on its fourth preview, which means that it will become a standard feature in the nearest future.
All right, cool. Yeah, there was another follow-up question, wondering about making use of any low-level libraries such as like Vulkan API for graphics, or CUDA, or OpenCL for computing.
So so the answer is, as long as the library has a C API, it's easy to start working with it right now. But if some of that has a C++ interface, or it's written in other programming languages, but which code could be compiled into a shared library that basically provides some interface, some external C interface. For instance, in Golang you have a CGO that compiles into a shared library. You can also use that. But anyways, if a library has a C++ API, you have to do a bit of work around that, which means you have to introduce another shared library that will wrap a C++ API, and then you will have to work with your own library, as with the additional bits of code, which is sounds similar to what the JNI was all about. But this time it's different. You didn't expose any internal JDK types to the C code. You only have a pure C or pure C++ code. Well, with the extent C, of course.
All right, thanks. Yeah, so I think that's all the questions. So yeah, thank you very much, Dennis. That was brilliant. Really appreciate you joining us tonight. Okay, thanks everybody for joining the stream as well. Yeah, no, brilliant. Thanks everyone for joining the stream, and hopefully see you all again soon.
Sure, likewise. Thank you.